All right, let's go ahead and go through the slideshow for this week's lessons, which is looking at the precise definition of a limit. And so we're going to try to understand the notation for finding the formal definition of a limit, and then determine a delta for an arbitrary epsilon given a linear function, and then determine a delta for an arbitrary epsilon given a quadratic function. So what we're basically starting with is the definition of a limit, and then using that to prove that certain functions have a particular limit. So we'll go ahead and start with the definition, which is on this page here. It says epsilon delta definition of a limit. Let f of x be defined for all x not equal to a over an open interval containing a. Let L be a real number. Then the limit of f of x is equal to L if for every epsilon there exists a delta such that if x minus a is less than that delta, essentially greater than 0, then this relationship holds. That is, f of x minus L is less than epsilon. Basically, one way to interpret this is if you choose a point that's very close to whatever value you're approaching within delta, then it should be true that your output is very close to the limit within epsilon. So as these get smaller and closer to the value you're approaching, these get closer and closer to the L, which is the output you're approaching. So you're approaching the point essentially from two directions. One is horizontal as you're getting closer to the horizontal point. That's the part that you're approaching over here. And then vertically, you're getting closer to L. So the arguments are really going to hinge on finding the appropriate delta and making an assumption about the delta that will then lead us to a conclusion about the function being less than epsilon. So a lot of these problems are going to start by trying to nail down some delta that's going to get us the result we want, because we're saying this is going to be true if there exists a delta that meets this specification. Okay, so let's see if we can try to do that with an example here. This is prove that the limit of 4x plus 1 is equal to 5 as x approaches 1. Okay, so all the work is here, but I'm going to try to do it on a paint screen, see if that helps us kind of talk through what it is that we're trying to accomplish. So let me see if I can share a new paint screen here. All right, so my what I'm trying to prove is that the limit of 4x plus 1, and forgive me, I don't have my touch pen, so I'm just using my finger here. As x approaches 1. Okay, so again, remember that we need to choose a delta that meets the specification that x minus 1 is less, that if x minus 1 is less than that delta, then what we are trying to show is that f of x, which is this function, minus L, is less than epsilon. Okay, so before we actually go into the proof, which we're probably going to do somewhere down here, we have to do some scratch work. Okay, so we're gonna do that here. Let me make sure I'm still sharing the right thing. Okay. And we're actually going to start with recognizing that we want to find something that is going to get us. So this is scratch. Oops. This is scratch work here. You'll often have to do scratch work on these problems. And so if I just do some algebra on that expression, what I find is that I end up with, what is this, 4x minus 4. And then I'm going to factor out the 4. And what I'm seeing is, or what I'm remembering here is that I want that to be less than epsilon. That's the epsilon there. But I'm also seeing the relationship here that I'm after over here, except it's got the 4 in front of it. So if I divide out the 4, then that helps me identify which delta is going to work for me. Okay, and so what I do here then is I let delta be less than or equal to epsilon over 4. And then I'm gonna go ahead and do the proof and start off with my assumption. So this here is my assumption that, and I mainly need to focus on the right side of this equation. That's going to be less than my delta. So I'm going to make that assumption because I've already picked my delta. And if I multiply both sides by 4, okay, and then this leads, I can basically distribute that because 4 is a positive number, and I'm left with 4x minus 4. Now these cancel, so I'm left with this is less than epsilon. And then finally over here, this is 4x plus 1 minus 5. Which is what I was trying to show. So I'm done with a proof after choosing the delta appropriately based on my scratch work, and then making letting delta be epsilon over 4 because of my scratch work, and then starting with my assumption. And then from there, I went on to complete the proof. Now, the proof in the slideshow is slightly different. It still arrives at the delta that we were after. So it's the same delta, and we find it basically the same way. So this is the scratch work. You also still start with the same assumption, but rather than manipulating it, then working off of the assumption, which is how I did it. I multiplied both sides by 4. We're starting off with the limit expression, and that's fine as well. And then after so this is f of x minus L, you simplify it, you factor out the 4, and the way you use the assumption in this case, rather than manipulating it to look like the expression you want, what you do is you make a substitution. You substitute the x minus 1 with a delta, and then you remember that you let delta be epsilon over 4, and then those cancel. So the proof is slightly different, but you still, in the end, are able to show that the absolute value of f of x minus L is less than epsilon. Okay, so here's another one. Let's go ahead and look at this one. It says the limit of x squared is equal to 4 as x approaches 2. Okay, so let's go ahead and look at this in the paint screen so that we can try to understand how to work with this one. Okay, let's open a new paint screen. All right, so this is the limit of x squared is equal to 4 as x approaches 2. Okay, so so we're gonna have to do some scratch work again to figure out what the delta is. And so what we'll begin with in this case is to help us figure out what delta we want. Let's go ahead and write down the relationship that we are hoping to arrive at, and that this is less than epsilon. And what I'm gonna do here is write this out in this way. So write this out as x squared minus 4 is less than epsilon, and minus epsilon on that side. And then I'm gonna add 4 to both sides. Again, this is scratch work to help us figure out what our deltas ought to be. So this is epsilon plus 4 And this is 4 minus epsilon. Okay, now I'm gonna take the square root of both sides of all sides. This should be a less than symbol, and I know it gets a little messy because I'm not using the right pen here, unfortunately. But I've got the square root of 4 minus epsilon is less than x, which is less than the square root of 4 plus epsilon. Okay. And I've got one more thing to do here, because if you recall, the relationship that I want to start off in terms of my assumption is that the absolute value of x minus 2 is less than delta, because of this 2 over here on your left. So I'm going to subtract 2 from both sides, actually from all sides. Okay, so I've got x minus 2 in the middle. I've got the square root of 4 plus epsilon minus 2. And over here, I've got the square root of 4 minus epsilon minus 2. Minus, that's a minus there. Okay, so now going back, I think we're ready for the proof part now. So we're gonna go with our assumption, which is that this is less than delta. And we actually have two choices for delta. They're both of these that we already selected through this process of scratch work. And so I'm going to take this. So we're working on the proof at this point. We're done with the scratch work. Okay. And this is going to be less than minus delta. So I'm just taking this expression that we have worked with before, that's absolute value, and we're just rewriting it with a minus sign. And then, so I'm going to take this piece, which is on the left. So this is minus the square root of 4 minus epsilon minus 2, because that's my delta, and less than absolute value of x minus 2 less than the square root of 4 plus 2 minus 2. Okay, and because this is already done in the slideshow, I'm just going to bring it back to the slideshow. So that is precisely this line here. Okay, so we're taking our assumption. We said over here, we must begin by making this assumption that's based off of the definition. Okay, then we did some scratch work to try to figure out what our deltas would be. And well, actually, so this is the line that I just wrote in the paint screen. Okay, where we took the assumption and wrote it out with a minus delta and the delta, took it out of the absolute value. We take our two possible deltas, and then with a little bit of algebra, so let's see, the first step is to distribute the minus sign on the left. Okay. And we don't need this at this stage because we're just working off of the whatever we've set delta equal to. And then we add 2 to all of it. Okay. And then we end up with this expression, and then we go to the next page. We're going to square everything to get rid of the square root sign, and then also, because remember, we actually want to work with, we want to arrive at this expression based on the assumption that being the absolute value of f of x minus L is less than epsilon. So we're almost there, because if I subtract 4 from both sides, then I can take this expression and rewrite it as an absolute value. And indeed, we have proven that the limit of x squared as x approaches 2 is 4. Okay, so I'm going to go ahead and leave it at that. I'm also going to post some really nice YouTube videos that should also complement the slideshow that I've given you. And then I plan on solving individual problems from the homework and posting 4 or 5 minute solutions on those. And hopefully that'll help you with the rest of this week. And we'll see you later.